So, very good morning. I'll be continuing from Charlie where he left. So, we'll be working on something called force field parameterization. So, you have heard about this force field, right? The parameters, what Charlie was mentioning about. So, we'll see how, from where, and how we get these parameters and how we can also parameterize some molecules using some techniques. So, one of the recommendation is that this is a book which is a standard book for molecular dynamics simulation. So if you would like to start from somewhere, this is a book you can start with. Very nicely written, very intense book. And from this book only, I have taken this picture just to warm you for the discussion. Is that so? There are three ways of doing any experiment, or three ways of doing any science. Currently, we have another term came in is a data science. So let's say another one here, which is data analytics, data science, and things like that. But if you want to do something like that, you either go and perform experiments, or you can do computer simulations. Yeah. So you can do three things, right? I mean, computer simulations, construct theory, or perform experiments. And the thing is that with the simulations, what happens is that it's very much dependent on the potentials you are giving, on the force fields you are giving. If your force fields are exact, the results are also exact. Means it's a very interesting concept there. And how exact you can build your force fields, that's the question. Let's say if you can do complete ab initio, a complete molecular dynamics, then most probably you are most of the time better than experiments, because all the external factors, right, humidity of the room, temperature of the room, or conditions of the experiments, those are controlled very well. So it's a given ideal situation. In theory, or you can do a computer experiment which can give you a fantastic result or better results than experiments. But there are a lot of ifs and buts, because the force fields, what we are going to show you, they're highly approximated. And then the theoretical predictions, often what we do, when you do a theoretical predictions, you do a lot of cut corners, right? You take a lot of assumptions. And after taking assumptions, you basically come to a point when you compare your theoretical predictions either with experiments or with simulations. So that's where how the theory grows. Now, this is the outline of the talk. So basically, we'll talk about a little bit about molecular simulations, and then what is force fields, some parameters and some targets, how we basically optimize those. And we'll quickly go to the conclusion. And if the time, if I get some time there, then maybe I can show you around a little bit of the online force field generators. There are a lot of tools from where you can generate force fields nowadays. So in the molecular simulation world, where we are standing. So there are two types of molecular simulations, generally what we can think about. One is a finite, one is periodic. So let's say if you are taking one molecule in gas phase, this can be a finite simulation. It might not be a periodic simulation. So basically in a periodic simulation, what generally we do, we basically consider box and keep a periodic boundary conditions. So basically it will look like a complete simulation or a infinite system. It's like a bulk. So always in a molecular simulation, the quest is going from a finite system to infinite system so that we can simulate something called bulk. Let's say if you are simulating 100 water molecules, if you are doing a molecular dynamic simulation, it will represent the bulk. It will give you the bulk properties of water. So that's the thing I would like to mention here. And then for both of them, you can have quantum chemical methods and classical methods. So today we are talking mostly on the classical methods. Quantum chemical methods we are not touching here. That's another type of simulations, much better simulations you can do, or much quantitative simulations you can do because you are doing it from ab initio. Now you have deterministics and stochastics. And in the deterministic area, we have our molecular dynamic simulations. So this is where we are in the tree. And because deterministic, because we are doing our simulations as a function of time. So time is one of the factor, and we can determine that how my system is evolving as a function of time. So now having said that, this is finally where I'm landing to Charlie's presentation. If I put them together, this is how it looks. So you have a molecular dynamics engine, right? I call it an engine because what you are doing, you are nothing but solving Newton's equation of motion, right? Force equals to mass into acceleration. So you're solving this equation, and to solve this equation, what you need is the term potential, the interactions between the atoms and molecules. That is what you need. And to get that potential, we are today here. My talk is about that how we are going to get these potentials. If you are not having these potentials, that means you cannot calculate the force. If you cannot calculate the force, you don't have the acceleration. If you don't have the acceleration, you don't have the velocities. And if you don't have the velocities, you don't have the positions, right? These are the equations which are interlinked. And if you don't have the positions, that means you are not propagating or evolving your system as a function of time, as a function of femtosecond time scale or a picosecond time scale. So that is what we are doing. So that means you have an MD engine, you have a starting structure. You have to start from somewhere, right? If you are doing a protein simulation, you have to have a starting structure of the protein, which you are getting from PDB databases, RSCB databases. So, and then you have to have a model. The model here is the meaning is the potentials. How is these atoms are interacting with each other, that you have to model to start your calculation, to have your calculations running. Once you run your MD engine, you basically get trajectories. So that is your snapshots or your movie, right? As a function of time, all the positions of all the atoms in X, Y, Z coordinate system, the Cartesian coordinate system, that is what we record. Once you record that, you can do three things. You can visualize those, means you can load your trajectory into VMD or PyMol, something like that. You can visualize. So if you visualize that, most of the times you understand how your system evolved, whether your protein and the ligand are interacting around that time, or the ligand has left the protein pocket or protein binding site. Those things you can already visualize if you have a long enough trajectory. Or let's say if you have a protein where your protein, one of the domain is moving a bit, you can already visualize maybe if you have a microsecond worth of simulations. You can do StatMech. So StatMech is very important, statistical mechanics. So you basically calculate using statistical mechanics or statistics, the hard numbers, numbers like what is the density of the system. Let's say if you are calculating water, if you are doing methanol, ethanol, you'd like to understand what is the density of the system, what is the melting point of the system, or what is the thermal conductivity of the system. All these calculations can be done using statistical mechanics. So use statistical mechanics to get hard numbers from your trajectories. Then the structures, semi-hard numbers. So semi-hard numbers are something like that. You get some structural properties out of it. What do we mean by that? Let's say if you are doing a simulation of lipid bilayer, and now you would like to understand that whether your head group of the phospholipid is surrounded by water, how many water it is surrounded by. So that is the first solvation shell. So if you want to calculate that first solvation shell, what you generally do, it's called RDF, radial distribution function. So that is your semi-hard number, and those things also can be done from experiments. So you can compare that. Structure factors can be calculated from experiment. So you can go and check your structure factor for certain systems, and you can compare that. So this is how full MD looks like. So this is the second part of it. Now, let's say what we generally do. Basically, this is nothing but doing an experiment. In your lab, you go take a beaker, put things in, increase the temperature, decrease the pressure, or you do something in a constant temperature and pressure, and calculate some properties, or try to understand some properties from your characterization units. So same thing is here in MD, is that you have your simulation box. You put in whatever you want to simulate here, water or protein or ligand and protein, and then you have the interacting potential, the force field here, and you are running, Newton's equation of motion at a constant temperature and at a constant pressure or at a constant, a chemical potential. So these are the different ensembles you can use for running your simulations. And if you can run your simulations at different ensembles, experiments are also done in different ensembles, so you can compare the data. You see, there is a very one-on-one comparison between experiment and simulations. But the question mark is that how we are going to get these interaction potentials and how we are going to validate those and how we are going to write those potentials and finally do the simulations. That's the first barrier you have to cross. Second barrier is that once you have run the simulations, then how you are going to analyze that. So the discussion today is how we are going to have these interaction potentials. So what is a force field? So, now the interaction between atoms and molecules, we have to have some mathematical expressions for those. And these mathematical expressions are written, and then we have to write it in a way so that we can parameterize that as well. So we have to do some amount of approximation for writing those mathematical expressions. And what are the force fields are used for? Different things, like you can have force fields generated for structural determination, conformational energies. You can have, simple things like rotational or pyramidal inversion barriers, vibration frequencies, molecular dynamics. So for various things, you can write different type of force fields or parameters. A little bit of a history. So around 1960s, in that time, the molecular dynamics basically started coming. And the first force field, the pre-1970, there was a harmonic force field. So all the atoms are interacting through harmonic interactions. And then around 1970s, the first force field came where, kind of a less than 100 molecules or 100 atoms were taken into account. And then they started doing these force fields, very accurate force fields for that. So very accurate force fields to calculate, say, vibrational frequencies and things like that. And then that's the time the macromolecular force fields also started coming. So that's the time when people started thinking about how to do protein simulations using molecular dynamic simulations. And present, we have force fields available mostly for all type of biomolecular systems. Mostly for all proteins, all lipids, you have force fields available, all RNAs, all DNAs. You can construct force fields within few minutes. You don't need to even go into hours to generate that, because there are tools available to do it. Well-known classical force fields. So this is the chart which you might remember for a while, because whenever you go to a conference of molecular dynamics or talk about molecular dynamics, this is what people would discuss, that which force field you have used for your simulations. So these are few classes of force fields. It starts from MM2, 3, 4. This is a molecular mechanics force fields for small molecules. This started around 1970s, around that time, to do some specific things for molecules, small molecules, And then the charm force field started coming, amber started coming, and OPLS started coming. So the charm is actually currently being highly used for biomolecular simulations, as well as amber. So amber and charm is kind of a competitive force fields which has been used for biomolecular simulations. And there are groups who are certainly working on charm. There are groups which are mostly working on amber. So there is another class of OPLS, another force field, which is OPLS. This is optimized parameters for liquid simulations. Let's say if you are not doing biomolecular simulations, if you are doing hydrocarbon simulations, or if you are doing, let's say, lubricant simulations, or if you are doing surfactant simulations, inorganic surfactant simulation, most probably the good idea to use OPLS force fields, because OPLS force fields are optimized for liquid simulations. Okay, OPLS also is available for proteins. You can also try for protein simulations as well. Gromos is one of the oldest, one of the older in this group. And again, this is a little bit united atom model type of a force field. And this is also used for protein simulations. Compass and TRAPPI. TRAPPI is very well accepted for phase equilibria kind of a simulations. Let's say if you are working with water or any liquid system, you are looking at VLCC, like vapor liquid coexistence curves, and then phase diagrams for liquids and things like that, then TRAPPI is one of the best force field to use. So you see, when I'm talking about force field, one thing I'm trying to mention is always for what it was developed. So it's very important that when you are, your system you consider, then you have to know which type of system you are doing, what is your target, what kind of properties you are going to look, and then which force field is best suited for those kind of properties. Let's say if you want to calculate surface tension for an inorganic surfactant, that is most probably best choice to go for OPLS. But if you are doing for a surface tension for a lipid, let's say organic lipid, then most probably it's not a bad idea to go for CHARM. So something like that is, that comes with your experience, and mostly you take an advice from your lab mates or from your supervisor that what type of force field will be best for this kind of systems. Okay, so another thing just would like to mention that whatever the force fields you have seen in my last slide, they are all class 1 type or type 1 force fields. There are type 2 and type 3 force fields are also available. And these force fields are kind of a many-body force fields. So there are complicated terms in the force fields, not as simple as the class 1 force fields. But soft matter simulations, where you have mainly carbon, hydrogen, nitrogen kind of atoms, organic molecules, you basically, mostly we try to stick to the class 1 force fields for biomolecular simulations. So this is the slide Charlie also showed you. So this is the molecule, and now we are writing that mathematical expression for telling you that how the atoms and molecules are interacting with each other. So that's the part from where you basically have to understand that which of the parameters are going into your simulations and how we are going to get these parameters. So if you see, this is a molecule. There are terms which are bond. There are terms which are angle. There are terms which are dihedral. And there are terms which are non-bonded interactions. So these are my non-bonded interactions. This is my non-bonded interactions. We'll go one by one. So this is a bond. So it's basically represent any bond here. Let's say this is a C1 and C2. There is a bond here. C1 and O4, there is a bond here. So if you want to represent these bonds, these are represented by this equation. You see, this is a simple spring, right? This equation is nothing but a spring equation. And then what are the two unknowns here? Two unknowns are K bond, which is the bond constant or the force constant in case of spring, and R0 is the equilibrium bond distance, right? Or equilibrium distance of a spring. So now this is your equation, and you need to know these two terms for each of these bonds in this molecule, right? So you need to know these values for all these bonds of this molecule if you want to generate a force field. Now, the angle. So angle is also vibrating, right? It is stretching and coming back. So again, that is also represented by a spring, you see here. And then you need to know the spring constant for the angle. So the force constant for the angle. And then you need to know the equilibrium bond angle. So that's your angle. So you can see now that O5, C1, O4, C2, C1, O4, C3, C2, O2, these are all my angles. So all these angles has to be parameterized. You need to know the force fields or this constant and this value for all your bonds, angles. So not only that, you need to know also the dihedrals. Okay, so I'll explain the dihedral a little more. So you have to, there are dihedral angles. So this dihedral angle potential is represented by a cosine potential. Most of the time it's a cosine potential because dihedral will be coming back to the same position after a rotation of 360 degrees. So that's why it is generally represented by a cosine potential. Then finally, the non-bond interactions. I have separate slides for this, so we'll come back to that. So now the potentials, if you see, I have written down all these terms. You have potentials for bonds, you have potentials for angles, you have potentials for torsions and dihedrals, you have potentials for non-bonded interactions. So now, basically, these four terms, the first four terms, we can say that these are bonded interactions. In force field language, we call it whatever representing is a bonding between the atoms, between the nearest neighbor atoms, which is the, bond is the first atom, angle is the up to second atom, dihedral is up to the fourth atom. So those are represented by bonded interactions. So we call them bonded interactions. And the rest, how there will be an interaction between this atom and this atom, or an atom from another molecule here. Let's say there is this is a liquid system, right? This is not only one molecular system. There are many molecules are there. That will be represented by non-bonded interactions because there are no connections between these two. So these non-bonded interactions are generally represented by Lennard-Jones and Coulomb. So Lennard-Jones is coming from your van der Waals interactions, and Coulomb is coming from your electrostatic interactions, right? Charge-charge interactions. So quickly, the bonds. If you see, I have represented some bonds. This is a C-sp3 bond. So if you take a carbon, if you take, say, methane or ethane, let's say, 2 carbon atoms, both are sp3 carbons. They are connected. This is the L0, equilibrium bond distance. This is the K value. So these are tabulated. These are well-known values. These are available in literatures. These are available in your MD software. Means if you are using Gromax, this is already available there. And always we represent in a harmonic term. So basically, most of the cases, you don't have bond dissociation. So if you are looking at a reaction, if your collaborator is saying, I want to look at a reaction, chemical reaction, you say mostly no. With this classical molecular dynamics force field, we cannot look at bond dissociation or a bond association formation. So now, these are the angles. Again, sp3, 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 109. You know that generally it's a tetrahedral molecule, so it's a 109. This is your K value for these different type of atom types, and so then the angles. So these are when you have molecules like alkane chain or alkane chain with a carboxylic acid or a amide group. These are well known. So these are well known, well understood, well documented in the literature, and well taken care in your software already. So you don't need to do it again and again. But if you happen to get into a new molecule, then your work will be to design these numbers, to get these numbers. Similarly, like torsion, so as I was telling you, this is coming back. So you have a potential like this, which is periodic in nature. So that's what you basically then write a periodic cosine potential, so which basically brings your periodicity is taken care, and it brings you back to the same potential. So other than that, we generally also add something like out of plane potentials. If you think of a benzene ring, and if you think of the hydrogen in the benzene ring, right? That's on that same plane. And if you are not having an out of plane potential, that hydrogen will not stay in that plane. That hydrogen will be, backward in some other direction. So you have to also add a out of plane potential. And also you have to add sometimes, some cases, improper potentials. Again, the example of benzene ring. If you are not doing that, the benzene ring will not be planar. It will be, it will be folded. So you have to have some out of plane potentials as well. So improper potentials, sorry. So now quickly to the van der Waals interactions. So now the van der Waals interactions, this is the atom-atom interactions which are intramolecular plus intermolecular. Think of a system where you have multiple water molecules. And these water molecules are interacting with each other. So how these atoms will interact with a molecule, I am sitting here, one molecule to another molecule, right? Each of these atoms will interact with these interactions. So what do I mean by IJ? So IJ is atom sitting on one molecule to an atom sitting in the second molecule, right? So let's say in this case, if you are taking an example of water, say hydrogen of one water molecule interact with the oxygen with of another water molecule. So that's your Ij. So you're calculating all these potentials from these kind of Lennard-Jones potential, whereas your sigma and epsilon is your term, which is your parameter. And again, most of the atoms are already been documented with sigmas and epsilon. And sigma is generally represented as a covalent radii of an atom. So it is basically a spherical atom is been taken, and then is basically representing a physical meaning of it is a covalent radii. Whereas epsilon is the potential depth. So where is the interaction is happening. And then you have the Coulomb interaction, Qi, Qj. And this Qi and Qj, these are your partial charges. In molecular dynamics, we have partial charges, right? The charges are not full charges, they are partial charges. So all the atoms would have some amount of partial charges. Let's say if you take water, is H2O, the oxygen would have a negative partial charge, hydrogen will have some positive partial charge, and the total charge will be 0. Then now let's say these sigmas and epsilons are atomic properties, because say every oxygen and hydrogen will have their individual sigmas and epsilons. Now if you have mixed system, now I'm calculating the sigma ij for between hydrogen and oxygen. How do I combine the sigma? What is my new sigma? So then we use something like a combinations rules. In some cases we use arithmetic means. In some cases is a GP, the geometric mean. So this is and it's a force field dependent. So if you are going from one type of force field to another type of force field, then these mixing rules are also changing. So you have to be also very much cognizant of the fact that which force field you are using and what is your mixing rule. So this mixing rule is, this rule, what I have written here is called Lorentz-Bartlott mixing rule. So this is your sigma, as I was telling you, that sigma represents your atomic covalent radii kind of a thing. And then epsilon represent you this potential. If you draw this potential, then there's a well, and this represents the energy of that well. So this is your, finally, your non-bonded interactions. So we have covered bonded and non-bonded interactions. So you can see now how many parameters you need. You need parameters for bonds, angles, dihedrals, out of plane, improper and everything for bonded. And for non-bonded, you need, for each atom, you need sigmas and epsilons. For each atom, you need Qi and Qj, right? So now all these things we have to translate into our force fields, and we have to do the development of the force field, right? So basically now you are in a stage that you have these atomic and molecular properties translate into the parameters. So what are the parameters we have taken? Atomic size, atomic charges, equilibrium distance, angle between atoms, and energy barriers for rotations between collective atoms to another collection. So this is your dihedral. So by doing so, you have your force field ready. So now the thing is that you have the force field ready for a molecular system, right? We have developed the force field for a single molecule. Now I have to go for a bulk system. So the idea is that now we have the option of changing the potentials or tuning the parameters as we go from a single molecule to a bulk. So that's what we generally do for optimization of a force field. Because when you design a force field or when you are writing your parameters, you are mostly writing for a molecule. And mostly these parameters are coming from experiments or quantum chemistry calculations. So therefore, what you can do, atomic properties should be tuned to reduce to the bulk properties, right? So whatever the atomic properties we have taken, they should be reproducing the bulk property. So to do that, we can therefore change those parameters or tune these parameters. Some parameters you can tune. You need to know the science or chemistry of that. When you are changing the parameter, you should not be changing the covalent radii so much that a carbon becomes a calcium, something you should not be doing. But there is always a scope. And we generally say that change the parameters which are non-observable. So in quantum chemistry, something called, there is a called observable and non-observable. So non-observables, the numbers can vary, like charges, partial charges. There are different methods, and the numbers can vary. Similarly, your sigma, the covalent radii, also can vary a bit because these are non-observables. So if you want to now optimize your parameters for a certain target, for a bulk, you can change the parameters. One thing is very important, force field parameters are parameters, should be regarded as a parameter. What do we mean by that? Is that sometimes there is a huge fight between the groups. You will see that this is for this molecule we have to use charm, or for this molecule we have to use amber. So these fights are very common, very often. But the thing is that it's within a limit, right? You are okay to change the parameters to fit or to match your bulk property, experimental property. Because most of the times parameters are developed, let's say CHAM, AMBER, or OPLS, for a certain target, for a certain experimental target. Let's say today, again, you come back and say that I want to calculate thermal conductivity of water. Maybe the force field coming from CHAM group, the water is not good enough to basically give you a good thermal conductivity. So you always can go in and change the parameters within a limit, right, within a boundary. So that's why this is a very important message, that the parameters are parameters, treat them as a parameters, and you can actually change the parameters which are non-observables. So not necessarily they are meaningful physical constants. So these are not physical constants. These parameters don't treat it like, gas constants or something like that. So but estimation of the parameters are important, and to go from molecules to bulk. So let's say I'm going from molecule to bulk, and the idea is that for that we are trying to calculate a bulk property. And as my presentation suggested, that I'm going to talk about a small molecule parameterization, which is very required because protein, lipids, all are solved. You will be mostly stumbling upon parameter development for small molecules because you will be mostly working on drug designing at the end of the day. So you need to know the parameters for small molecules. So, and then if you are designing a parameter for small molecule, then you have to have a target. You take a small molecule, let's say a ligand, and need to know which is the target you are going to design the parameter for. Let's say density of the bulk system, or enthalpy of vaporization, or in most of the cases for drug designing, it's solubility, right? You need to know, or you would need to design a force field which gives you the good solubility in water. Otherwise, your simulations can go completely wrong. Solubility, log P, lipophilicity, all these things you have to look at. So this is the water. I'm now showing you the water molecule. So this is the structure, OH, the distance, HOH, 104. And then flexibility. So these are my OH frequencies, bond frequencies, angle frequencies, dipole moment, excluded volume, and dispersion forces. This is attractive, right? So simple water molecule. So then basically what you do generally is that you take the structure. So you take the bond distance of 0.97, angle like 104, and you basically convert your this OH and the HOH into a K value using the equation, and you know the K value, so you have all the parameters. From dipole moment, you can get the partial charges because you know that the dipole moment can be correlated with the partial charges. And you can sometimes get from dipole moment, or sometimes you can also get it from quantum chemistry calculations, the partial charges. You get the partial charges, and then you basically design this equation. So you need to know the sigmas and epsilons. And if you know all these sigmas and epsilons, most of the cases, sigmas come from covalent radii, as I told you, and epsilons come from, again, from quantum chemical calculations. So once you have that, you have now the parameters, the starting parameters. And using the starting parameter, you basically start running a molecular dynamic simulations. And once you run a molecular dynamic simulations, you basically have many water molecules, and your potentials are in a sum. So basically, this is the all potentials which are acting on each of these molecules, and then intramolecular. So inter and intermolecular potentials, you are summing it up. And once you have the sum, you basically get the V. And using this V, you are calculating these forces and you are propagating the molecule. So basically by doing so, then you have many water molecules and then you are basically scanning the potential energy surface. So this is how you basically now, once you scan these potential energy surface and you get the properties, or you have the trajectory, from the trajectory you get those properties out. Now you match your density or match your heat of vaporization and things like that. Once you match it, you know that okay, it's giving you the experimental value or not. If it is giving you experimental value, good enough. If you are not getting the experimental value, you go back and change some of your charges or sigmas or whatever the parameters we think that would change, and then if you change those parameters, what will be the effect on the target properties. So this is, now I'm quickly shifting a gear a bit, just to show you that all the force fields which have been developed already, they also use a very similar roadmap for getting those. So this is like a roadmap for CHARM 27, very well-known force field. You will be coming across quite often. So if you see initially, what they started doing is that initial geometry model compound. So you basically, the geometries of a compound, if you have a new ligand or a structure of a new compound, you have to have the geometries of the compound. So that geometry is coming from quantum chemistry calculation. So this is where it is, you see QM, MP2, 63G, this is a quantum chemistry notation of writing. So you are basically optimizing a molecule to get a structure of that, get a chemical structure of that molecule, correct. Once you get that, you basically also calculate the partial charges. Partial charges are again coming from, in CHARM, coming from quantum chemistry calculations. See, this is what I was mentioning, that you calculate the partial charges again from a quantum chemistry calculations. Then these partial charges are coming in, you're calculating the van der Waals parameters. And then once you are done with that, you have the bonds, angle, torsions, and impropers. These you have incorporated in your potentials. Bonds and angles for a very first molecule, generally once it's not known, either they can come from experimental values, because you have IR and spectroscopies and all these things. From there, you can calculate the frequencies, and from there, you can calculate the constants, or you can calculate from quantum chemistries as well, right? These numbers go in, then you do a condensed phase simulation. This is your bulk simulation. Then you basically self-consistently solve these two. One is bond angle torsion, another one is the partial charge in atom. So you self-consistently solve it against your data, which is your experimental data, a target. Target can be density, heat of vaporization, or things like that. Or in your case, if you are looking at ligand for drug designing, you should be looking at solubility or cohesive energy density, which is very similar to your rate of vaporization as well, right? So this is what you are going to look at. So this is the chart, yeah. Yes. Yeah, in quantum mechanics, that's why it's called ab initio. There's no force fields are there in quantum mechanics. So you're solving Schrodinger equations. Yeah, yeah. There is no force field. Yeah, there will be a potential you will be using. So you see, in quantum chemistry, there are different methods. You can use DFT, you can use Hartree-Fock, you can use, this is written here is MP2, the molar perturbation theory. Here it is ab initio, there is no potential goes in. You see, they solve Schrodinger equation for all the electrons of a system. And from that, basically, you get back the parameters. So now, the CHARM. So I just wanted to show you that, how different it is, right? Means why I mentioned that you can go and change the charges, or you can go and change the, say, sigma values. This is where the table shows, say, I have the atom types here for a molecule. So these are atoms. This is the charge calculated from Mulliken charges. Mulliken is a well-known method to calculate charges from quantum chemistry. This is the ESP charges. This is another method to calculate the charges from quantum chemistry. And this is, you see, charm, what the charm uses in charm force field. So if you see the numbers, C2, C carbon atom for certain carbon atom, Mulliken charges is 0.63, minus 0.63, ESP charges is minus 0.8, and charm uses minus 11. Such a variability, right? So you'll see that when you do a quantum chemistry calculations and you're calculating a USP charges or Mulliken charges, then you'll see that there is when you transfer those charges, you have a lot of ways you can change the charges. Mostly we try to keep the dipole moment correct. So that's one of the factors that we try to do is the dipole moment correct. So, but you can change. So some thumb up rules. Minimum optimization by analogy. So this is what we mean by that. Let's say you hit in a new molecule and you say that I have learned from this workshop that I have to do it from the beginning. No, it's not like that. So you try to find out the parameters from literature for any molecule you are doing. Then you try to find out what is missing in those parameters, which dihedral angle is missing, which charges are missing. Then only you go back and try to do, quantum chemistry calculations for getting those parameters, number one. So number two is that if you want trying to do maximize that, so maximum optimization, so if you want to do too much of optimization of these, this is a time consuming thing, right? So you basically mostly don't get the parameters as correct as, let's say, experimental certainties. Don't go beyond that. There are, say, if you're calculating PG, or if you're calculating melting point, there is an experimental uncertainty already there. So your parameters also can be generated in a way so that it be in this experimental uncertainty. You don't need to, beat to the date to find out the number, exact number. It's not like that. And the choice of parameters based on your goals. So that is very, very important. What your target is. If your calculations is ligand binding to protein, it's solubility. If you are looking at surface formulation for your drug, then most probably is interfacial tension, IFT. So these are your targets. So that's most probably you have to understand when you develop a force field. So I want to skip it because I'm already another 10 minutes I have. I just go quickly to this is water. I have shown you this water, I just want to mention one thing here is that, as I told you that there are different types of force fields. There are different OPLS, charm, amber, and all these things. Also, there are small molecules. There are also large number of force field types available in the literature. Let's say in a water case, in a water molecule, has around 250 force fields available in the literature. And this is a website where they track if there is a new water force field is coming out. This shows you the variability of the parameters for a target property. Why people came up with so many force fields? This is taken a snapshot from that. You see, there are more than 250 water models. Because some force field would give you ice 1, some force field will give you ice 2, some force field will give you the correct melting point of ice, some force field will give you correct boiling point, some force field will give you correct surface tension. So it's like, it's like a zoo. So that's what the message is here, that the small molecular force field is really, really kind of a, when you hit on something, look for the target, what you are trying to achieve from that. Okay, so as I was telling you, the target properties, then this is one of the example I would like to show you for ethylene oxide. Again, this was done quite a while back. So what we have done, we have used a simplex technique, so method which automated the force field development. So whatever I told you is like, it sounded like manual, right? You can automate the whole process of optimization. And basically what we started with is quantum chemical calculation. We got this is 256 molecules, not atoms, sorry for the typo. And then basically you take these molecules and did one quantum chemistry calculation to get the structure. Once you get the structure, you get the bond lengths, angles, and their, K values and all the values from the literature. Charges, we took a range. So if you see the charges of oxygen, carbon, and hydrogen, we have taken a range. And we try to fit that charges, which will be the best charge to get the properties correct, right? So then basically we calculate the charges from Gaussian. So Gaussian is a quantum chemistry package, which is well-known quantum chemistry package. You can use that, or you can use an open source called NWChem. Then basically from the Gaussian output, you will get these, SCF done, where, these kind of energies you will get for the molecule. And also you will get the charges. So charges are, these are coordinates. I'm trying to find out where the charges. These are, I must have not written the charges here. So you can visualize it with Gaussian output, and you can get the charges from this Gaussian also package. I haven't written that here. So once you have that, then basically you have the Lennard-Jones parameters. You have the atomic charges, different atomic charges, and the target was density and heat of vaporization. So we were trying to optimize the force field for density and heat of vaporization. So then we basically did simplex, iterations. It automatically changes the parameters within a bound and takes and optimizes the target properties. So then if you plot the heat of vaporization and then density together in the same plane, this is our target, and you see that how basically with simplex round that has, that basically sample the space. Similarly, the parameters, how that been sampled, different LJ parameters, Lennard-Jones epsilon and Lennard-Jones epsilon for oxygen. This is for carbon. And then finally, the, what is the output? So the category 1 properties are like here, the liquid properties, the vapor properties, liquid properties, and the vapor properties. And this is your heat of vaporization. So basically, we calculated, the target was to calculate the density and heat of vaporization. We got quite a nice value with, this is the experimental values, and this is the calculated from the optimized force fields here. However, if you see the other things, like we have calculated the Cp, beta, viscosity, thermal conductivity, other points, they don't match very well with the experiments. It can give some of the properties quite well, as it is optimized against densities and heat of vaporization. But if you take for heat capacities and beta, so then basically you see that there are good amount of deviations from your experimental data. So you see the vapor phase beta for your ethylene oxide, and this is your experimental. So you see there is this kind of problems you will always get. Force field optimized for something, you're using the same force field for some other properties, you might get into a trouble. Okay, so I stop here for this part. Just want to quickly, another 2 minutes, 3 minutes I have. Okay, I sounded very negative that it's very difficult sometimes and all these things. So, but at least I give you a message that maybe will help you out in quickly running your molecular dynamics simulation. So fortunately there are auto generators or online servers. I just quickly run through 1 or 2 so that you know that okay, to start with something there are some available things are available. So these are your auto generators. Lickpergen, this is OPLS-based force fields. So if you are looking at small molecules, it's not bad. It gives you quite well. If the parameters are there, then there is no problem. If the parameters are not there for a particular molecule, then it will throw you error and say that the parameters are not available. You are on your own. Swiss param, if you are doing protein ligand binding, it's a charm 27 parameter which gives out. You just upload your structure. It will give you the force field file for GROMACS or UNCHARM, sorry, and UNCHARM as well. Polypoidgen, this is for polymer, OPLS-based polymer. So if you have a large polymeric system, this is a not bad starting point at all. BOSS is basically part of LeakPurgeon. This is a method which goes into LeakPurgeon. DRG, and ATB. ATB is not a bad tool at all. ATB has around 400,000, if I'm not wrong, 400 or 40,000. ATB is around 400,000 molecules are already force fields are deposited there. 400,000. So if you are, in that domain, go and look for it. And those are optimized, by the way. These force fields are quite good in ATB. So you will be learning about GROMACS from Aisha in the next session, and then Travis. So in GROMACS, you will see that there is a step where you have to set up force fields and make topologies. You will learn how GROMACS does it. There are internal tools in GROMACS as well, which quickly you can generate force fields for proteins or lipids very easily if you have the initial structure. So you will learn that. And what I will do is that I will upload this slide deck in Slack, both the slide decks. This has a lot of content that how the force fields are look like, that how it is written and all these things. Please have a look. If you have any questions, I'll be happy to answer later on as well. Thank you. ATB, it's a mixed. Yes, it can have anything. ATB is mixed. I think this is LeakPurgeon.
So I was wondering what force field parameters they use in that CRO drug.
This is ATB. And there you will get OPLS, CHARM, AMBER.
All of them.
All of them. And some molecules even have multiple. You have CHARM, OPLS. You can just go there and choose whatever you want.
Oh, that's wonderful. And the second was, you see in the docking that we use such simple generation of partial charges. Do you know, if we replace those partial charges by force field, we'll have a better result at docking? Has anyone done that?
The charges, I try to say that if you are doing a docking, try to calculate the solubility for the molecule. And if you have the experimental solubility parameter for that particular molecule.
I see.
Then if you want to calculate the solubility, then mostly you basically fix the charges. You tune the charges and get the charges and the epsilon a bit so that you can get the solubility correct. Or you can get the cohesive energy density as well, heat of vaporization as well. So these are the three things. If you are correct, then the docking, post-docking MD, if you want to MD, that MD will be pretty good. MD of energy calculations will be, state of the art. Those energies will be very correct.
Okay, so start with some crude charges in docking, but then tune it with solubility and other stuff too. Okay.
Because you are going from docking, you are not having any solvent. You are going from docking to MD, where you are introducing a solvent. And the force field for the ligand has to be very good to basically reproduce the solubility of that molecule nicely. Otherwise, what will happen? You might, that molecule might not be, not stay in the bound form, but still it will stay in the bound form because the solubility, what it predicts was completely wrong. Yeah.
I'm gonna confirm that the force field is the best option for my system.
For which force field is the best option for your system, right? Yeah, that's a very tricky question, actually. It's there are dinner fights over it. So it's some groups will say always it's CHARM, some will say AMBER. I cannot answer it like that. So you basically, what happens is that I generally do it for myself is like that. I take an advantage of where I can get my force field quickly. Let's say I have a molecule, I want to have a force field. I look into CHARM, I look into amber, I look into OPLS. Mostly if it is a biomolecule, I look into CHARM and amber. And then if the CHARM gives me the force field, full force field without any missing parameters, I go with CHARM. If I don't get it there, I jump to amber. And then if amber gives me the force field, I go for amber because you have the parameters already available. One message is that don't go and redo something which is already available. So then basically take it up. And amber and CHARM are for biomolecules, so it's quite okay to take it up. If you are doing some liquid simulations, formulations and things like that, inorganic things, then you will always get into trouble. The materials kind of a subject, yeah. Okay, thank you. Thanks a lot. There is a question. Thank you. No problem. Please go ahead. Yeah.
So I may have missed this, but how do you said we can do this for larger molecules also, like DNA and RNA?
Yes. CHARM member of OPLS, everybody has DNA, RNA, proteins, mostly all fatty acids. Yes.
So how do you calculate like the combined effect of all the atoms in the molecules for like as a force field together? Like, will they change, or is it just calculated as somewhat of a simple summation?
Okay. So if I have understood your question correctly, you would like to understand that, if there is a protein force field available, whether that is already been tested for all the atoms in a protein to a target property.
Yeah.
Yeah, most probably something like that. So the idea is, yes, when the force fields were built for, say, proteins or RNAs or DNAs, those were tested well against their secondary structures. They're pretty good in giving you the good quality secondary structure, means the helix will be always helix, beta sheet will be always beta sheet. So the secondary structures, the whole protein structures will be reproduced pretty well. That is well understood, well tested force fields in the literature already for biomolecules.
Okay.
For bulk systems, bigger systems. All these collection of atoms and molecules, what I have shown you today, that the force field development and all, these are for new molecules. Let's say if you come across a molecule where the force fields are not available.
Right.
Right? There are already force fields that are available for certain class of molecules, and mostly biology is covered. Okay, let's say if you are doing something completely new, then you have to maybe get your force field done.
Okay.
Yeah.
As Sudip said, that for the secondary structures, we always test again the secondary structure. But with the recent advancement and understanding that disordered proteins are very important for biological activity, and all the force field that you are looking at they were not developed against disordered protein. However, there is a new force field, came from D. Shaw's group. New means like a couple of years back, which can handle both secondary structure and disordered protein together. So if you're working with disordered protein, there is a new one with the similar philosophy. So yeah, there's all good.
Thank you. Yeah, thank you.